For this problem, we're given a function and we want to find the derivative. So we're going to use the formal definition of derivative, which means to find the derivative of our function, we're going to compute the limit as h approaches 0 of f of x plus h minus f of x divided by h. And we're using our function square root of x for this. So when we compute the first part of this is the f of x plus h part. Remember, that's telling you to take x plus h and to substitute it into your function, the square root of x. So that becomes the square root of x plus h. Then the second part tells us to just subtract. Here we're just subtracting f of x, the original function. So that's minus the original function, square root of x, all divided by h. So we want to try to do direct substitution, but of course we can't divide by 0. So we're going to algebraically manipulate this expression. And we're going to do that by multiplying by the conjugate. So the conjugate of the numerator is the square root of x plus h plus the square root of x. And then we're going to multiply by that in the denominator as well. That way we're really just multiplying by 1, so we're not changing the value. And sometimes it helps people to go ahead and put big parentheses around the numerators so that we can keep track of our work a little bit more easily. Remember, we still have to keep writing the limit as h approaches 0 until we actually do our direct substitution. So when we multiply the square root of x plus h times the square root of x plus h, we'll just have x plus h. The outside and the inside terms will subtract out because they're opposites. And then the last is negative square root of x times positive square root of x, which will just be negative x. Now the denominator, I recommend that you leave the h factored out and just leave it as h times the quantity square root of x plus h plus the square root of x. So now we'll simplify. We see that our x's are going to subtract out. That'll leave this h in the numerator, which will then divide out with the h that we have in the denominator. So that's going to leave us with the limit as h approaches 0. We now have 1 in the numerator and the square root of x plus h plus the square root of x in the denominator. So now we're to the point where we can try our direct substitution again, which is great because when we substitute here, we're substituting 0 in for h, which we can do that now because it's not going to give us division by 0. So we'll end up with 1 divided by the square root of x plus the square root of x, which we can then simplify by adding the denominators, the values in the denominator, and that'll give us 1 divided by 2 square root of x. So this is the function that we end up with for our derivative. And remember, this is a function or a general formula that will compute the slope of the original curve. The original curve was the square root of x. And this derivative will compute the slope of the square root of x curve at any point. So the rest of the problem says to determine the domain for both functions and then compare their graphs. So let's start with the domain of the original function, the square root of x. So for the original function, we know we cannot have negatives inside of a square root, but 0 is okay. So that tells us that for our domain, our x values need to be greater than or equal to 0. So in interval notation, that would be a bracket, 0 to infinity for the domain. However, for the derivative, even though we still have a square root, it's in the denominator of the fraction. So on this one, 0 will not work. So in the derivative, our x values just need to be greater than 0. So in interval notation, our domain is going to be a parenthesis 0 to infinity. So here are our corresponding domains. And then it would be fine for you to go ahead and use your calculator to graph the derivative. However, I'm hoping you would be able to graph the original function without a calculator, that you would recognize the basic shape of a square root graph. We know that the square root of 0 is 0, and the square root of 1 is 1, and then the square root of 4 is 2. So you could plot a rough sketch of the original function. And if you use your graphing calculator, notice I'm only focusing on the first quadrant for both of these because of the domain restrictions. So go ahead and pause the video and type this function into your graphing calculator, and then come back and take a look at the shape of the derivative function. So the derivative function looks like it has a vertical asymptote. So it kind of looks something like this. Now when you graph it on your graphing calculator, initially you might make the mistake and think that the graph stops, because the graphing calculator does kind of make the graph look like it just stops there. But if you were to zoom in and adjust your window, you would see that this curve actually does increase, and there is a vertical asymptote here on the derivative, for the derivative function. So the next discussion point is, why is there a vertical asymptote there on the derivative? And if we go back to the original function, it has to do with what's happening right here near the origin on the original function. So if you were to think about what the tangent line might look like, the way I have my graph drawn here, my tangent line would look something like that. But I just free-handed this graph. So if you were to take your calculator and actually zoom in right here on the origin, you would notice something about the graph of the square root of x. I'm going to erase what I have here. While I'm doing that, go ahead and zoom in on the origin of your square root of x function. And if you zoom in on the origin, the graph starts at 0, 0, but if you zoom in maybe 2 or even 3 times, what you're going to notice, get the idea here, is that near the origin here, there it is, right there, that near the origin, that these tangent lines here are becoming more and more vertical. And we know that the slope of a vertical line is undefined. So what that tells us is that at the origin, the tangent line would actually be vertical. The slope there is undefined, and that's what causes the derivative then to have this vertical asymptote, because that means that the derivative is undefined at 0. And see how these y values on the derivative are growing and getting bigger and bigger and bigger? That's because the slopes near the origin, the slopes are getting larger. So that's why the y values on the derivative grow. And the derivative is undefined at 0, because what we have happening at the origin, that's important for you to note, is that we have what's called a vertical tangent. And whenever a graph has a vertical tangent line, that means that the slope is undefined, and that means that the derivative is undefined there as well.